Welcome back, everybody. In this section, we're going to be working on still hypothesis testing, but this time we'll be doing claims about a mean. And in this section, we're going to focus on the more realistic or usual case where the sigma is unknown, because usually you don't know the population standard deviation in practice. So that will be our focus. So the players here, N as always, will be the sample size, X bar will be the sample mean. The mu of the X bars, that is the mean of the sample means, ends up being the population mean, and that's taken from the claim and is used in the statement of the null hypothesis. Okay, so to do this, we need the population to be either normally distributed or either that or to have the sample be at least 30 in size. An important piece will be our test statistic, which will be T for this because the sigma is unknown, so we'll be using T for the bulk of this section. And that will equal X bar minus mu X bar divided by S over root N. So that will be an important part, that test statistic. Okay. We'll use technology or the t-distribution table with the degrees of freedom given by n minus 1. Using the table, it can be a little tricky to find p-values. If you're not using technology like a calculator or StatCrunch, usually the critical value method is going to be easier. Okay, so we'll have to see how that goes. Okay, all right, so first of all, just a little practice of finding critical values off of the t-distribution. So here, let's say we want to find the critical value that we would use for a left-tailed test with an alpha of 0.05 and an n of 21. So if the n is 21, remember that the degrees of freedom will be n minus 1, and so 20. So we'll be looking in row 20 on our t-table. And then we're told on this one that the alpha is 0.05 and it's left tail. So it's only one tail and 0.05. So area in one tail and 0.05. Where those two intersect, 1.725. So that's most of it. But one thing you're going to have to be careful of is that this thing says that it is a left-tailed test, right? And the t-distribution is centered at 0. Remember that the t-distribution only has positive values in it. So because this thing is a left-tailed test, and we just use symmetry to give us the negative values, the value we actually need for this is negative 1.725. The positive 1.725 is what we would use for a right-tailed test. Remember again that the t-table is going to give you just positive values, not the negative values. You have to keep in mind whether you're doing a left or right tail test to help you locate the correct value. Okay, let's try that again. Let's say that we want to find critical values for a two-tailed test this time with an alpha of 0.01 and an n of 16. So again, our degrees of freedom will be n minus 1. So we'll be 15. We'll be in row 15 on our t-table. This time it is a two-tailed test, so we're going to be looking in the two tails row across the top. Our alpha is 0.01, so area in two tails, 0.01, that's the first column. So first column, and then row for 15, 2.947. So then there's going to be two critical values for this. There will be positive 2.947 and negative 2.947. And those will be our two critical values. All right, so we've practiced looking up critical values. Now it's time for us actually to execute a full hypothesis test. So let's try this one. Here it says an insurance agent says that the mean cost of insuring a car like yours is more than $875. A simple random sample of 9 similar insurance quotes has a mean cost of $917 and a standard deviation of $62. we're to test the agent's claim with an alpha of 0.01, we'll assume the population is normally distributed. All right, so I'm going to start by making the hypotheses. Remember that the null hypothesis is the one that is assumed true. The agent says the cost is more than 875. So that will be the mean is greater than 875. Since it's greater than, we're going to put that in the alternative hypothesis. And then the null is going to be that it's equal to the 875. All right. So there's that. A little picture next. So this one is a right-tailed test. Our N is 9 cars, so our degrees of freedom will be 8. So we need a right-tailed test. The degrees of freedom needs to be 8, and our alpha is 0.01. So let me go get our value off the t-table. All right, so with the degrees of freedom of 8, we'll be in row 8 of our t-table. We're doing a one-tailed test with an alpha of 0.01. So one tail, 0.01, that will be column 2. So where those meet is 2.896. Okay, so now it's time to calculate our test statistic. So that will be T is equal to X bar minus mu X bar over S over root N. So our sample mean was 917. The hypothesized mean was 875. The standard deviation was 62. And then the sample size was 9. Okay, so let's go ahead and calculate that. Okay, 2.03. Okay, so that's our test statistic. 2.03 doesn't fall in our rejection region. Okay, remember the distribution centered at 0, 2.896 was our critical value, and 2.03 then is going to fall to the left of 2.896. And so we're going to fail to reject our H0. Okay, and then if we're not rejecting the H0, that means we are not supporting H1, because remember, it's one or the other. And if we were able to reject H0, then we'd say, okay, well, that supports H1. But as it is, we're not rejecting H0, so there's insufficient evidence. Let's just say not enough. There's not enough evidence to support the agent's claim. Okay. All right, so we did this test using the critical value method. And I want to kind of show you how the p-value method is going to work. I'd mentioned before it's a little trickier with the t-distribution, but let's try. So we saw that our test statistic was 2.03. So if we're going to try the p-value method. So our test statistic ended up being 2.03. And the way that this works is we would look in the table and try to figure out what that area is. And that area is going to correspond to our P. And the problem with the T table in comparison to like the Z table is that there's just less rows, less values, because we have to deal with the degrees of freedom idea. For any 1 degrees of freedom, there's only 5 different areas to choose from. So with our degrees of freedom of 8, taking a look in that table, notice that, let's make that nice and big. Okay, so we're looking for 2.05. Okay, there is no 2.05 in this row. Okay, that's one we need. So the thing is, where would that be if there were one? Notice that on the right, we get 1.397, then it goes up to 1.86, 2.30, 2.8, then 3.3. So it's getting bigger as you go right to left, or smaller as you go left to right. So there isn't 2.05, what was that, 2.03? Writing 2.03. There isn't a 2.03 in here. We just have to figure out if there were, where would it be? So considering that these are in order, it would have to be in here, right? Between 2.3 and 1.88 or whatever that is, right? It'd have to be in here. So since this thing is a one-tailed test, right, it's a right-tailed test, then that means that the p-value would be in between 0.025 and 0.05. So the p-value is between 0.025 and 0.05. Since we were supposed to test this thing at the alpha of 0.01 level, and we know that p is bigger than 0.025, it definitely has to be bigger than 0.01. So we would reject, fail to reject the H0. Okay, based on that. Like I said, using the p-value method with a t-table is a little trickier just because you have to figure out where it would be, because you're not going to be able to find the exact number actually. It can be a little trickier, but usually doable. All right, so let's go on to another example. Okay, so here it says an environmentalist estimates that the mean waste recycled by adults in the US is more than 1 pound per person per day. So let's start with hypothesis right away. So the mean is more than 1 pound. The alternative is that it isn't more. Okay, so we want to test the claim and find that the mean waste for a sample of 12 adults, so the n is 12, so the degrees of freedom will be 11, is 1.2 pounds with a standard deviation of 0.3 pounds. So again, at the alpha of 0.05 level, we want to know if we can support that claim or not. So let's start by making the picture and figuring out what that critical value is going to have to be. So our test is right-tailed, and our alpha was 0.05. Okay, so if our test is right-tailed and we have an alpha of 0.05 and a degrees of freedom of 11, then that's going to be 1.796 off the table. All right, and then next we want to know what our test statistic will be. So that will be x bar minus mu x bar over s over root n. Sample mean was 1.2. Hypothesized mean was 1.0. Standard deviation 0.3. And then the sample size was 12. All right, so let's get our statistic. That's 2.31. Okay, so that's 2.31, which is higher than 1.796. Okay, so that's higher than 1.796. And so based on this, we're going to go ahead and reject the H0. And if we're rejecting the H0, that supports the H1. So we could say there's enough evidence to support the claim. Okay, so that will do it. Now what we're going to do next is rework this thing using the p-value method just for comparison purposes. So up here we have the hypotheses, we have the test statistic, which was 2.31. That's really all we need here. So the t was 2.31. We knew that our degrees of freedom was 11. Okay, and so this test was right-tailed, and for this p-value, we want to figure out what that probability is in that one right tail. So again, taking a look at our degrees of freedom of 11, which is that row, notice that the bigger numbers are on the left and the smaller numbers are on the right, so they're in order. We want to figure out where 2.31 would be. So it's smaller than 3.1, smaller than 2.7, but bigger than 2.2. So if we had like a nice custom-made t-table with another column in here, we would think 2.31 should be in there when the degrees of freedom is 11. So let's see what one tail area that corresponds to. Well, that's between the 0.01 and 0.025 column. So that means that the p is at least 0.01, but is less than 0.025, and that's the part that matters. Since the p is less than 0.025, that is less than our alpha, which was 0.05, and so we are able to reject at H0. And then the conclusion is the same, that it supports the environmentalists' claim. All right, so let me stop the video here so that it's not super long. We're not quite done with this section. We have more examples, but we'll do that here in a few minutes.